this way then. Yeah, thank you very much. And good morning, everyone. It's very nice to be here in person and to have this opportunity to talk a little bit about the project I've been working on in person. So my name is Alexander Wojtczak. I'm a PhD candidate from the University of Cologne. And as the title of the talk says, I'm going to talk a little bit about the study we've been done on the bracket gamma gas emission in a sample of T-Tauri stars that was observed with VLTI gravity between 2017 and 2021. And maybe if you're not very familiar with okay, now, if you're not very familiar with the topic, then first let me introduce to you what physically motivates the study. So when we're talking about bracket gamma radiation, as was already mentioned in the talk by Karim Perrault yesterday, we're talking about processes, something that traces processes at the very innermost region of the inner gaseous disk, and specifically in low mass YSOs, the idea of the bracket gamma emission region is very closely associated with the idea of magnetospheric accretion and other accretion-driven processes like winds launched from the inner region, because specifically the bracket gamma hydrogen emission requires certain temperatures to even be produced. And in the relatively cool T-Tauri stars, unlike in Herbig's, we don't see them in the environment, in the inner disk. We need specifically magnetic heating mechanisms to produce this kind of radiation. So magnetospheric accretion in itself, if you're not familiar, it's currently the dominant paradigm of accretion models for low mass YSOs. Basically, the idea is that since T-Tauri stars are very strongly magnetic, they show magnetic field strengths on the order of 1 to 2 kilogauss. You get a truncation of the inner disk. So that magnetic field prevents the disk material from spiraling inwards in the disk plane. And instead, you get these kind of funnel flows that are arched, and they transport the material onto the stellar surface at relatively high latitudes. So the question we are trying to examine here is very much whether we can pin the bracket gamma emission that we observe in our sample specifically to magnetospheric accretion or to more extended processes like the disk winds or even maybe stellar winds that are launched from the polar region. And to examine this question, we are primarily examining the size of the emission region from our interferometric observables. So we determine the size of the pure line emission region from the visibilities that we recorded with gravity. But we're also going to look a little bit more at the spectra, because we are expecting certain features to see, for example, this kind of P Cygni profile that you see here in the lower left, where we see this kind of absorption feature that is caused by infalling gas. You would see this for sources that are observed at relatively low inclination. So where the infalling gas that is optically thick would block out parts of the star. And we are also, as already Valerio talked a little bit about in his talk, going to look at the photocenter shifts, because the photocenter shifts track the kinematics of the gas, and we have analyzed the distribution of these shifts for the different velocity components across the bracket gamma line. And you see this a little bit in the animation here on the lower right, where the white cross signifies the pure line photocenter of the image that you're seeing here, tracing the photocenter at different velocities of the funneling flows. The image that you see and the animation that is built upon it comes from an imaging cube that was provided to us kindly by our dear colleague Benjamin Tessot from IPAC in Grenoble. And we have done, in addition, some work with these radiative transfer image cubes. We try to determine, first of all, we use them very much to determine what actually would be a typical photocenter profile for such a purely magnetospheric accretion system, because it's not actually very clear just by thinking about it intuitively, especially when you go to different inclinations. And we've also done some work in terms of computing synthetic observables from the models. I'm not going to necessarily talk about that in detail today, but I will come back to that and refer back to that when I talk a bit about the results of the sample. So our sample itself consists of 7 different T-Tauri stars, one of which was observed twice, once in 2018 and 2021. That was RU Loop. So we have a total of 8 data sets, essentially. Most of them are strong accretors. Only TW Hydra and Dua 44 are on the weaker side in terms of their mass accretion rate. They were all observed with the UTs of the VLTI, because the ATs are generally not sensitive enough to detect the bracket gamma feature. And then we proceeded to do our analysis on a channel-by-channel basis. And we tried to, first of all, determine the size by fitting a simple geometric model, a Gaussian disk, across the different channels based on the pure line quantities. So we extracted to remove the continuum contribution to really track purely the gas emission, and did the same exercise also for the photocenter shift, of course. So we're tracking the pure line photocenter shift based upon the pure line differential phases. So before I get to those results for our sample, I would like to talk a little bit about the spectra that we recorded with gravity. So there is a common trend among these spectra for most of the sources that we see, that there's a certain asymmetry to the feature. And you see there's an excess of blue radiation in the wing, so an excess in the blue wing that is not there for all the sources, but for many, especially for the strongest emitters. Now, there was a bit of question internally in our group whether this is really an additional component, a blue shifter component, that in addition to the magnetosphere could contribute to the bracket gamma, or whether this is maybe an expression of this kind of absorption feature that was described before that we would expect from the pure models. But based on our work on the image cubes, it seems, so at least for the strong emitters, it seems unlikely. It does not, the imaging cubes do not reproduce the feature that we see for the strong emitters. It's a bit less clear for the case of, for example, TW Hydra, where, and maybe also DWA 44, where we do see a little bit a dip that could signify absorption in the red, although it's not trivial to talk about this in terms of just pure visual inspection. So in terms of the sizes that we determine and their variability across the line, we broadly categorize 3 different classes of sources among our sample. One, we have the case of a very compact emission in the bracket gamma, that is TW Hydra. We compare the radius, the half-flux radius that we determine specifically to the so-called co-rotation radius. So the co-rotation radius gives us a necessary criterion to determine how likely it is that magnetospheric accretion can even occur or can contribute dominantly to the bracket gamma emission. And you see the co-rotation radius in these plots is signified by the red line, and the color squares then give you the sizes that we determined in each channel that we are looking at. And you see that for TW Hydra, so the plot on the top right, it's all very much within this co-rotation radius. So this is a further indication that for TW Hydra, we probably have a very strong magnetospheric component to it. Then we have 2 sources that are very much more extended than the co-rotation radius in the cases of AS353 and DG tau. So it's more likely that our bracket gamma emission is tracing some kind of extended structure in form of probably a disk wind launched from the inner disk. And then we have a lot of sources where it's not so clear. We get something that is broadly on the order of the co-rotation radius or of similar magnitude than the co-rotation radius, but not to the same degree as, or not to the degree as we would expect maybe from purely magnetospheric accretion. So in these cases, I think it is likely that we are looking at a system that is a bit more complex and where we have multiple origins of this line emission that contributes to the overall visibility profile. And the situation is not dissimilar for the photocenter shifts, although the profiles themselves are not as easily categorized because there's not such a nice clear criterion. We look again at the case of TW Hydra in the top right, where we see a very compact clustering of photocenter centroids that is very in agreement with what we see in the model for such a polon source. This is also something that maybe if you recall, you saw in the animation when the image went through this kind of polon configuration, you see this very close concentration of points. So this is in agreement again with the magnetospheric accretion scenario. But for the other sources, it's not so clear. If you look, for example, at the case of RU loop, which are the middle panels on the left, the 2, so these are the 2 epochs of RU loop, you see this almost kind of crescent-shaped structure. That is, first of all, significantly less extended than what we would have expected from the model for this specific inclination. And also it shows this kind of curvature that is not really reproduced in the purely magnetospheric accretion scenario. So yeah, it is a bit more difficult to classify. And then, of course, we have a lot of sources where, since the differential phases are generally more noisy than the visibility amplitudes, we associate larger error bars with them that make it difficult, or more difficult at least, to speak about trends as we go across the line. Yeah, so in conclusion, this is more or less the takeaway message I would try to convey here. We have this general categorization between sources where we have clearly extended emission, where we have clearly compact emission, and then a lot of sources where we probably have different sources of contribution to our bracket gamma system. Based on the plots that you see here, which show the size of the emission region in terms of the stellar radii, you see that we have this kind of for many of our sources, except for our two strongest accretors, we do see this kind of clustering almost across the about 5 stellar radii region, which is something that is typically associated with the magnetosphere. So there's typical sizes for magnetospheric system, for typical magnetic field strengths in T-Tauri stars. So this further indicates that magnetospheric accretion, at the very least, plays an important role, even if not an exclusive role for many of these sources. And I think I will leave it at this point. And if you have any questions, I'll be happy to answer whatever I can. So thank you for your attention.
Okay, thank you very much. Are there any questions for Alexander? Check online. No? Okay, I was wondering, do you think there's any, do you see any follow-up observations or follow-up modeling that could help you disentangle the more complex bracket gamma emission regions?
Yes, it would be. So I think this is also the next step in our cooperation with the people from IPAC and Grenoble, that we would like to have imaging cubes that include a wind contribution, basically, so we can make a more informed assessment on whether this is a realistic, these visibility profiles that we see are a realistic product potentially for a more complex system like that.
Okay, great. Any further questions? Oh yes, we've got a question from Alexis Mata. So how would you benefit from bracket alpha observations in the L band?
I'm not sure. I'm not sure actually if this is also something we have currently a model for. I mean, I know Benjamin has worked on a variety of spectral lines for H alpha and also I think some CO lines, but I'm not sure if he also treated the bracket alpha. I'm not sure that if this necessarily solves the issue we currently have with disentangling the different contributions, but I would have to think about it.
Okay. Sure, fair enough. Great. Okay, so we do have time for any more questions, but also if we'll give some people to think, and then we can always continue to discuss on the Slack or offline. So let's thank Alexander again.